Hello everyone, thank you very much. Today I'm going to introduce you to multi-view 3D point tracking. The world we live in is dynamic, and as human we can effortlessly perceive these dynamics. I argue that the intelligence agents, in order to interact with the environment, also have to have a perception of these dynamics. This then enables applications in robotics, in the surgical room, as well as more general in biology and neuroscience for arbitrary point tracking. So to begin with, I want to emphasize that efficiency is important for these applications, especially for robotics. Precision is important for all applications. I also argue that the robustness to the camera setup we have is equally important. For example, if you have multiple cameras, that the methods are robust to the number of cameras, the position of the cameras, etc. First, I'll give you a systematic overview of point correspondence problems in 2D as well as in 3D. So starting in 2D, we have feature matching. Very important problem, very well studied, important for 3D reconstruction, structure for motion, etc. But it's only tracking static points. Moving to dynamic points, we have optical flow, which is tracking the apparent motion in videos. However, it's only tracking for the short term, frame to frame. Then we have point tracking, which is an extension of optical flow, where we try to track arbitrary surface points throughout the whole video. This is all tracker, the current state-of-the-art tracker in 2D point tracking, presented at ICCV as well. You can check it out. In moving to 3D, we have seen the scene flow, which is an extension of optical flow to 3D. However, it's again tracking only frame to frame. We have monocular 3D point tracking, which received a lot of attention in the past years, past 2 years especially, but inherently it can't leverage multi-view input. The problem we are focusing on, the task, is multi-view 3D point tracking. In this setup, we have synchronized cameras, and because of having multiple cameras, this offers a better coverage of the scene and therefore a better precision. These problems have only been studied from an optimization perspective and require a dense camera setup of 27 cameras or even 100 cameras. This is why we introduced the first feed-forward 3D point tracker for multi-view setups. It's called MVTracker, and it runs in 14.9 frames per second. We can work with as few as 2 to 4 cameras and already leverage the multi-view nature of the data. Compared to monocular baselines, we can directly leverage the multi-view input and learned end-to-end priors. This allows us to set the state-of-the-art across multi-view 3D point tracking benchmarks. At the core of our method is to fuse the information from different cameras into the same 3D point cloud. So this is how the point cloud looks like. The colors are representing the features that we uplift to 3D to get this feature point cloud. And on top of this, we then learn a data-driven prior end-to-end. We do this using a transformer. And for this, we also have to contribute training datasets. We contribute multi-view Kubric, as well as pre-process other datasets to contribute multi-view 3D point tracking benchmarks to evaluate the performance of different methods. Due to the design of our method, which works in this 3D point cloud, we are flexible to the number of cameras used, as well as how these cameras are arranged in 3D space, also to the depth source being used. Compared to prior works, which focus on computing correlations on grids and triplanes, we directly compute the correlations with k nearest neighbors in this point cloud space. So more formally, this is how we define the task. We are starting with RGB videos from synchronized cameras, for example, 4 cameras, and with depths. The depth is from a sensor, for example, Kinect, or it's estimated with off-the-shelf methods such as Duster or VGGT. We also assume having a calibrated setup, including intrinsics and extrinsics. Then on top of this, we will run MVTracker for randomly sampled points to get the trajectories on the right. More precisely, we estimate both the trajectories as well as the visibilities as output. Visibility says whether the point was visible or occluded in any of the views. So let's take a look at the pipeline. For the input, we have query points. These can be sampled randomly, perhaps from the depth maps. Then the video RGBs as well as camera calibration. First, we take the RGBs to produce feature maps using a shell of CNN, which is enough to learn discriminative features. We also take the RGBs as well as the camera calibration to estimate the depth maps. So these depth maps will be estimated with off-the-shelf methods, or if we have Kinect or other sensors for depth, we can also use this directly to improve the performance. Then we'll back project these points and associate each with the feature from the feature maps to get this 3D feature point cloud. To do the tracking, we initialize the trajectories, as well as the features and the visibilities. And then we'll take the transformer, which will do the iterative updates. For this, we first prepare the inputs, so the positions, current positions, as well as features. We'll take the k-nearest neighbors around these current estimates of the positions and compute the correlation with those neighbors and feed everything into the transformer. The transformer outputs a residual update for both the position and the features. And we repeat this 4 times to get the final positions and the final visibilities. So we predict logits for the visibilities. Compared to various baselines across different sets of methods, we achieve the best performance across the evaluation datasets. First, starting with multi-view Kubric, which uses simulated depth from Blender, we achieve 81.4 in average Jacquard, which is a metric combining location accuracy and visibility accuracy. We get similar results on DexYCB and Panoptic Studio, which are real-world datasets. Due to the design of our method, our accuracy will improve with more cameras. And this is because we fuse everything in the feature point cloud and can easily leverage the added information and better coverage that we get from having multiple cameras. For example, this is performance in 1 camera, and we go up to 8 cameras with the estimated depth using Duster. Similarly, we can perform well and get stable results across different camera placements. So this includes, for example, these placements A, B, C, where we pick different subsets randomly of the cameras, and we'll get stable results across these sets and by a large margin better than the best baseline. These are some qualitative results comparing first the ground truth and our method on the top, MVTracker, and the bottom we have spatial tracker version 1, and the triplane baseline we devise by extending spatial tracker. The red lines indicate errors. Here's another example. I also want to point out that we can work with different sources of depth. So this is an example with using Blender simulated depth. We get very good results. This is a Kinect camera, which gives both RGB and the depth. However, if we don't have any kind of depth available, then we estimate it with off-the-shelf methods. For example, on the same sequence, if we estimate the depth with Duster, we'll get the depth on the bottom, which is much more jittery. And often, using off-the-shelf methods can result in failures. So this is how the depth estimation looks like. It's very jittery. We still are robust and better than baselines to some degree to this jitteriness in the depth. But if we have perfect depth, for example, from a studio capture, then the results look very pleasing, very good. So the main takeaways for MVTracker is that it's the first feed-forward 3D point tracker for multi-view. It fuses the information from multiple cameras by creating a 3D feature point cloud. Because of the design, it's robust to the number of cameras, the placement of these cameras, as well as moderately robust to the source of the depth. And it significantly outperforms baselines. The main limitation is this coupledness with the depth estimation and the fact that many failure cases in depth estimation will result also in reduced or failed performance of our tracker. Also, we only tested so far in bounded scenes. And our training is based on synthetic data, so having more data, especially real data, would improve the performance much more. I want to thank my collaborators and thank you for your attention. That's all.